Hello, everyone. Welcome to CYBR 708, Cybernetic Systems Design and Dynamics, Learning Activity 8, and we're going to be going into adaptive control and learning systems. And for this one, for this learning activity, we're going to be talking about adaptive control. And I will kind of dive into a little bit of computational learning theory or machine learning, again, just to kind of give you a high level in terms of machine learning methods, and then if you're one of my MLAS students, of course, you're going to get a lot more. We're going to be diving into more detail on machine learning systems, so I wouldn't, if you're not part of machine learning and you're, say, cyberhuman or space systems, then this will be great because I'll keep it high level for us for design and dynamics. Adaptive control, much like data, you can't do adaptation to a system, or you can't control the motor effect of a system if you don't have a DAQ. And so your DAQ system is integral to adaptive control. So from an architectural perspective, they all work together. So your control system that is adaptive will also include a DAQ system to help it be more effective in its adaptation to an environment. So it's essential, and so especially when we're talking about like UAVs or UGVs that are uncrewed aircraft vehicles or uncrewed ground vehicles, autonomous air, autonomous ground vehicles, whatever they are, that there's just so much more potential for them in their ability to navigate complex environments if they have a good DAQ, which then of course optimize them for adaptive control. Let's see. So there's, it's not just for me to just say, oh yeah, you should have an adaptive control system. And there's one thing for that for us to just say, yeah, of course, something, if I'm building an autonomous system, or if I'm building a mobile robot, or if I'm building a industrial robot, or if I'm building a software system, or if I'm building whatever the autonomous system is, whether it's bodied, unbodied, tethered, untethered, you name it, right? Adaptive control systems, there's multiple different systems. So you have to kind of do your homework on what makes the most sense for the control system. And a lot of times it's not a one size fits all. It's not like an MRAC is going to be better than an MPC. You're usually going to have some form of self-tuning. So you're going to usually have some form of MRACs with MPCs, with STRs, and or newer neural networks. So where I'm going is, do know that there are they're functionally specific adaptive control systems. You got model reference adaptive control, MRACs. You have STRs, which are self-tuning regulators. You have model predictive controllers, MPCs, adaptive sliding mode controllers, and then you have neural network based. Now this is not exhaustive. There are many adaptive control systems. This is just to say that there's these are the main ones, the primary ones you're going to come into. But you do want to do some research on this, right? And find out like what is your adaptive control system? What are you building out for your control system as it relates to your architecture and your research design? Let's see. Okay, so now from an adaptive control system, I do want to switch over, and that's high level. Let's talk about learning systems, and then learning systems in cybernetics. And so again, when we talk about cybernetics and artificial intelligence, we've already kind of covered that they used to have a shared common core back nearly 80 years ago. And so moving forward from that time, that I feel like they're coming back together. And so it's a good time for us to talk about learning systems and cybernetics. And so when we talk about machine learning, we've got supervised, unsupervised, reinforcement, and deep. And so, and of course, just like the adaptive control systems, no one size fits all, especially for for a very advanced autonomy. It's rare that you're going to have like a system that just works off of supervised, or one that works off of just unsupervised. Now there is a caveat to that, that the newer large language models, these really large, um, um, uh, they're deep learning methods for machine learning. They are kind of getting into, but um, I don't want to split. I don't want to get too far into the weeds, but deep learning models start to create differentiated architectures within them. And I know I'm kind of speaking high level, but it's kind of like when I create a deep learning model and it's like, let's say it's a large language model. These things are so large that what ends up happening is the structures that they start to create specialized structures within the deep learning models, that you end up developing all these different interesting structures within it, kind of like the human brain. So you get different types of gray matter, right? Your corpus callosum versus your prefrontal cortex, your Wernicke's area versus your um, let's see, versus your corpus callosum, right? Those kind of things. So there's just all kinds of different stuff as it relates to your brain areas, right? And their specialization, like vision, like your occipital region of your brain for vision processing, right? That happens in the back of your brain. And so there are structures that are built for vision processing. And so there's kind of like large language models develop, and they create specializations within their architecture. So that's just a little bit of extra info on that. But again, I don't want to get into too much detail beyond that. I may have gone a little bit further into it, but I hope that was helpful from a deep learning perspective in large language model. Okay, so let me back up. So the four that you have here are supervised, unsupervised, reinforcement, and deep. And supervised requires training data. Unsupervised doesn't require training data. Reinforcement doesn't require training data, but it does eventually, but it becomes conditional on training data. So reinforcement learning, in other words, I start off with no training data, and then I can reinforce it after I get a series of I can do reinforcement on the data as it comes in, and I can negatively reinforce the data or positively reinforce the data to create a negative or positive effect. So reinforcement is kind of, while it doesn't require initial training data, it will become conditioned on that training data, and so hence why you have reinforcement and reinforcement learning. So usually for learning systems, especially in our world, you're gonna have multiple. It's an ensemble. Usually there's going to be some kind of ensemble method. You're going to use 1, 2, 3, 4. You're going to pull them all together, and then you're going to create, a learning output or some kind of learning system that's able to make decisions or predict the future. Okay, so here's just a further refinement of that in terms of unsupervised learning, where there's clustering. Supervised learning typically will typically follow a path of, again, you have to have training data to make a prediction. And a lot of times supervised follows almost, I would say, I get this question a lot too. When it comes to machine learning, what's the math? And a lot of times the math is, there's two types of math that are largely involved in machine learning. And it's statistics and algebra. Those are the two. And algebra is usually, it's linear regressions, or regressions. Let me just say regressions, because I can have polynomial regressions, I can have linear regressions, and then I can have all kinds of different versions off of that. But usually it's some form of regression. And then semi-supervised learning, and then reinforcement learning. But almost all of these follow some kind of statistical some stats and or algebra. And so with that, um, I think I don't want to spend too much more time on this. In that I don't want to dive too far into the details. But if you are one of my machine learning students, definitely hit me up afterwards, and of course we'll learn more about this in your elective courses as it relates to machine learning. For cyberhuman systems and for your space systems students that are out there, yeah, if you're interested in learning more, again, we're here to help, and so definitely feel free to reach out. Okay, so let's talk about algorithms here real quick. So from a supervised learning perspective, a lot of times you'll have, there's just a lot of different algorithms out there. I haven't listed all of them, but supervised could be a neural network. Unsupervised could be a clustering algorithm. Some common ones for unsupervised learning clustering algorithms are going to be like principal component analysis, or stochastic nearest embedding. T-SNE is what it's called, and that's what you see over here on the right is actually a T-SNE algorithm, and that's a clustering algorithms. That is different from classification. Clustering is different from classification. Clustering occurs when I take data and then I do it based on no training data, right? And there's no training data involved. I just look at the existing data that I have with no prior history, and then say, okay, these should be grouped together based on characteristics that I see in just looking at the existing data pool that's been given to me. No training data has been added. Classification is different, where I provide labeled data and then I say, okay, now classify them based on the data that I've provided historically. So that's the difference between clustering and classification. So classification is a supervised learning task. Clustering is an unsupervised learning task. Then you've got reinforcement learning, which you have max-Q or Q learning. There's different algorithms for that. Reinforcement learning, the easiest way to learn about that is I can negatively reinforce something or positively reinforce something. So for example, if a very simple thing is helping you wake up in the morning. If you're a coffee drinker, you're positively reinforcing your ability to wake up in the morning. So then what happens is over the years, you continue to positively reinforce your waking up through a cup of coffee, to the point where studies have shown that even the smell of coffee will help you wake up, because you have become positively conditioned to Pavlovianly conditioned to be reinforced to wake up when you smell coffee. And that is through reinforcement learning. And then of course you have deep learning and neural networks, which also comes back to supervised learning. But deep learning doesn't mean it's a deeper, more robust learning method. It just means that it is actually deep comes from the fact that we're using hidden, very expansive hidden neural network pathways that are hard to illustrate. And a lot of times we have no idea what happens when we turn them on. We don't know how the structures are going to differentiate once we turn on a deep learning model. So that's where the deep comes from. It's kind of like, think of it as like the ocean. When you create these really expansive deep learning models, they have millions of hidden layers, and so billions of hidden layers, and so it can get kind of complicated quickly in the deep learning world. So that's where the deep actually comes from, is the visual from that perspective. Okay. Next up, we'll do a couple case studies and then we'll wrap this up. So case study for adaptive control system and then learning system to help improve flight behavior over time through training data it might capture. So having a learning system and an adaptive control system is actually quite critical for autonomous drone navigation. It's pretty, it's a perfect use case. If you're interested in learning more about the way that those work. I actually threw a paper in here that I found kind of useful, adaptive control for quadcopters. And so I think that might have some usefulness. And I think for the aerospace safety folks out there, this is something that might be useful too, for flight systems in general, not just for autonomous drones, but for flight systems and the adaptive control and fly-by-wire systems that exist out there and have been existing for a really long time use both adaptive control as well as machine learning models to help fly aircraft that otherwise are harder to fly due to their control surfaces. So and or keeping the pilot safe now because of newer aircraft, like I would say newer, but even aircraft that have been around since the 80s. So for example, like the F-16 actually can maneuver in such a way that is dangerous to the pilot. And so they actually had to dumb it down, right? They had to keep, because the pilot can pull, the airframe can pull more G's than the pilot can handle. So they have to be careful. So that they created a lot of adaptive control and machine learning systems in there to provide feedback to keep the pilots from injuring themselves in flight. Okay, so you also have healthcare monitoring diagnosis, right? You have learning systems in healthcare to adapt to individual patient data. You also have adaptive control systems that are applied to medical devices to help optimize or enhance specific treatment outcomes. And so there's a lot that goes into hospitals, especially when we're talking about diagnostics and therapeutics. And so when we talk about learning systems and adaptive control systems, it also expands up into the organizational level. Like how do you move patients effectively from one part of the hospital to the other? How do you triage them in mass casualty events? How do there's just a lot of things that can be done for adaptive control at a macro level is probably the better way to say that versus a micro level at the diagnostics and therapeutics level in terms of device monitoring. So a lot of opportunity here. So this is something to kind of keep in mind in that regard. Okay, last up, and I'll be wrapped up with lectures for this week. So challenges for adaptive control is data quality and quantity, the automation and being able to get quality data and the quantity of the data in a timely way and in a consistent way is definitely still a challenge. And I think integrating artificial intelligence into that and it go hand in hand. So your determination and your AI's ability to make determinations and to create strategies and think ahead is only as good as the incoming data that's given to it. Just like humans, right? Just no different. So if I give a human bad data, they're gonna make bad decisions. That's just it's plain and simple. If I give them biased data, humans are going to make biased decisions, right? So it's important to feed whatever that AI is, whether it's a natural AI like humans or an artificial AI that we create, that's been created. It's important to feed it lots of data from different sources, and that's what makes an intelligence, whether it's a natural intelligence or an artificial intelligence, it makes it makes decision making that much better on the output. Their end effect is going to be of higher quality if you provide better data from more sources. There's always going to be bias in data, but you can't get away from it. But what you can control for is the breadth of data. So I think that's one of the biggest challenges for the future. Is providing broad quality, robust data from multiple sources to both AIs and NIs. I'm just going to go out there and say it. So natural intelligences like humans, as well as artificial intelligences, they will operate better with a broader set of data, right? We just will. Um, I think that's an interesting trend for the future, and will help in that regard. Okay, so that's all I got for challenges. That's all I've got for the lectures. Last bit for public service announcement: I will be handing you off to your next set of professors. They will be in charge also of the next set of assignments, and but I will still be involved in the course, and I'll still be monitoring the course and managing the course and its outcomes. So if you have any questions, do feel free to reach out to me, but also feel free to reach out to your next set of instructors. I won't be dialing out completely. Again, I'll still be here. So if anything pops up, definitely reach out to me. But also don't forget, you also have other professors that are in the mix here to teach your next set of modules. So I enjoyed it, and I look forward to seeing how all the projects come out, and look forward to staying in touch with everyone. That's all I've got. Thanks. Take care.